So now in this problem, we're being asked to predict what is, rank them according, say, to increasing boiling point. So we're going to talk about that, and then I'm going to give you the boiling points. So first, this molecule, let's analyze the molecular formula. So here you have three metal groups. So this is trimethylamine. Trimethylamine. And it's got 3 carbons. And here you have 9 hydrogens and 1 nitrogen here. This is ethyl methylamine. So this is a tertiary amine. And here, because to know that, we will see how many of the H's in ammonia we have replaced. This is ammonia. Here you have replaced all of the 3 H's by methyl groups. So that's a tertiary amine. As for functional group. Now this one, you have replaced 2 of the H's by R groups. One is ethyl and one is methyl. In listing alphabetically, we're going to say ethyl, methyl, amine. And molecular formula will be 1, 2, and 3. And so C3. And H's you have here 5, and 3 is 8, and 1 is 9. And so notice they have the same molecular formula. And this is, as we said, a secondary amine. Lastly, this molecule is, notice 1, 2, 3. So this is propylamine. And it is a primary amine. If you compare that to ammonia, you have replaced only 1 of the 3 H's in ammonia by an R group, so it is a primary amine. And what else? What is the molecular formula? 1, 2, 3 carbons, so C3. And here you have also 9 H's and an M. So same molecular formula, different connectivity. These are constitutional isomers. And of course, they're going to have, because they have the same molecular formula, they will have the same molar mass. We know that the trend in general, for example, in alkanes, as we increase the molar mass, going butane, pentane, hexane, the boiling point was increasing. But now, when you analyze constitutional isomers, the same molecular formula, the same mass. So let's look at the functional groups then and the type of intermolecular forces that we have. So here, when you see trimethylamine, you have bonds of the type nitrogen and carbon, which are polar. So we would say nitrogen is more electronegative. So my dipole, and I have 3 dipoles like that, will be oriented the following way. So pointing towards the nitrogen. So if I make a drawing, say more showing the shape, I'm going to say this is my lone pair, and I'm going to say methyl, so similar to ammonia, right? So that's my structure, and all of the arrows here will be pointing towards the nitrogen. So this molecule is polar. And now, it's polar, but in all of these molecules having carbon and hydrogen, we will have London dispersion forces. But that's the weakest. Remember that in intermolecular forces, this London dispersion forces of van der Waals is weaker than dipole-dipole. Talking about permanent dipoles. Remember that? These are fleeting dipoles here. So non-permanent. Dipole-dipole is a permanent dipole moment in a bond. And lastly, the strongest in, and say, non-ionic compounds, but covalent compounds. We're going to have the hydrogen bonding. So now I see here in trimethylamine that I only have the strongest force. The strongest intermolecular force is dipole-dipole. This is for this molecule. Yeah. Now let's analyze ethyl methylamine. Now I have a hydrogen attached to a nitrogen. And for when hydrogen bonds, when you identify that you have a hydrogen bond, here you should have a hydrogen attached to either an oxygen or to a nitrogen, so a very polar bond. So that this is, for example, interacting with, I'm going to just draw water, for example, and that will be, say that here I have two R groups, so a primary amine. That'll be a hydrogen bond. And again, the hydrogen must be attached to a very electronegative atom. That exists also in hydrofluoric acid. But in most organic molecules, what you're going to see is hydrogens attached to oxygen or to nitrogen. So that interaction is stronger than a dipole-dipole. So going from weakest to strongest, I'm going to go London dispersion, then you increase that interaction going dipole-dipole, and the strongest being hydrogen bond. So this is where we are. When you have ethyl methylamine, you have one of such hydrogens attached to an electronegative atom. So you can have this interaction. Say that I have another molecule, and here I will have, say, methyl and ethyl. So that's another molecule, and you have that interaction. So definitely, you have an interaction that is the strongest. So the strongest interaction here is you still will have London dispersion and dipole-dipole, but then you add hydrogen bonding. So I expect that the boiling point here would be larger than that. So now let's analyze propylamine. In this case, I have two of these H's attached to nitrogen. Now we'll have more chances to do hydrogen bonding, and say that I draw one of those. So I will have a nitrogen here, and I'm going to say NH2 just to simplify that drawing. That's another molecule. But I have chances also of hydrogen bonding here. And so I have more opportunities, more chances to do such interactions. So more stronger intermolecular forces in here. So my prediction would be that propylamine will have having a stronger overall intermolecular forces. This should have the higher boiling point in this series. This would be, again, more chances of hydrogen bonding. Than, for example, ethyl methylamine. So I predict this boiling point is higher than ethyl methylamine, and this is higher than that. So I'm talking boiling point. So let's look at the numbers. This is understanding the intermolecular forces. Now I'm going to give you the boiling points for that. Trimethylamine, boiling point here is 3.5 Celsius. Ethyl methylamine is, let's write it here, 37 Celsius. And propylamine is 49 degrees Celsius. So notice that it's increasing. As we have said, we have the same mass. All of them are amine, but as we are increasing chances for other intermolecular forces that are stronger, so hydrogen bonding, and even more chances to do that, then let's say the interaction between molecules is stronger. So I need to put more energy to break those and go from the liquid phase to the gas phase.